Hi, welcome to our YouTube channel. Please subscribe. So today we are going to talk about CPU pipelining, focusing mainly on the core idea behind it and how instruction execution happens inside a pipeline processor. But before, let's imagine a very famous example. Imagine that 4 people, they decided to complete their laundry. Each of them will need time for washing, drying, and folding. For washing, each of them will take 30 minutes, for drying 40 minutes, and for folding, they will spend 20 minutes. Therefore, each person will spend half an hour for their laundry completion. So the question is, how do we manage to do the laundry in a lesser time? To answer the question, let's put everything in a table and see what if we do every person's laundry after another's. So here we have time till midnight from 6 p.m. and task order. First, person A takes their laundry and it goes through washing, drying, and then it folds, and it takes half an hour to do that. Next, person B does the same, washes, dries, and person C does the same, and person D finishes their laundry. But it takes time till midnight, and we don't want to spend so much time for laundry. So we come up with a technique called pipelining. The person A starts washing their laundry and they finish their laundry after 30 minutes. But we don't wait for the person A to finish both washing, drying, and folding. Person B starts washing their clothes right after the person A starts drying their clothes. And when the person B stops washing and starts drying, the person C starts washing their clothes, and instructions are completed one after another. All the tasks are completed in 3 hours and 20 minutes. So what is CPU pipelining? CPU pipelining is one of the most important concepts in computer architecture because it explains how modern processors achieve high performance without increasing clock speed dramatically. CPU executes instructions in steps, and to understand why pipelining is needed, let's first look at how instructions executed in a non-pipelined processor. In this approach, the CPU executes one instruction completely before starting the new one. So let's take a quick look at the traditional processor. We have a program counter. From that program counter, we get an access to instruction memory. And from that instruction memory, we get the instruction, and then we look at it and decode what kind of instruction it is. Meanwhile, we could be looking at our registers. Once we have read them, we are going to feed them to the LU. We're gonna do the add or subtract or the XOR, and the decoding logic will tell the LU what to do. Once we get the result from the LU, we could be done and write the result to the registers. Or we could have a load or a store instruction. So in that case, what the LU have computed is actually the address that we use to access our data memory, and what comes out of the data memory is what we use to write in our registers. So you can kind of see that the instructions are going through 5 phases. We go through fetching, we go through reading, decoding, LU, memory, we access the memory, and finally we write the register. In total, we approximately are using 20 nanoseconds. So how to apply pipelining? Here we have fetch, decode, LU, memory, and write parts of this processor. So what happens is that in cycle 1, instruction 1 goes through fetching process. In cycle 2, instruction 1 goes through decoding process. And in cycle 3, instruction 1 goes through LU. In the fourth cycle, instruction 1 goes through memory, and in cycle 5, it writes to the register. So every instruction will finish in 20 nanoseconds, ideally, if we don't do the pipelining. But if we apply the pipelining here, in cycle 1, instruction 1 will be fetching, but in cycle 2, when the instruction 1 moves to decode part, the instruction 2 starts fetching. When the instruction 1 moves to the LU, instruction 2 can start decode and instruction 3 can start fetching. Once the instruction 1 leaves the pipeline, very soon the instruction 2 will leave the pipeline, and so on. So to calculate this throughput, we'll divide 20 nanoseconds by the number of instructions by 5, so each instruction will be completed by 4 nanoseconds. It means that the first instruction will finish in 20 nanoseconds and the throughput is equal to 1 instructions by 4 nanoseconds. That is how long it takes for instruction 2 to leave the pipeline after the instruction 1.
Hello, and now I'll be explaining pipeline hazards in computer architecture. Pipelining is used to increase performance by allowing multiple instructions to overlap in execution, and this is a classic 5-stage pipeline. Each instruction goes through instruction fetch, instruction decode, execute, memory access, and write back. Although pipelining improves performance, it also introduces some problems called pipeline hazards. And a pipeline hazard is a situation where the next instruction cannot execute in the following clock cycle. And because of hazards, the pipeline may need to stall, flush, or use extra hardware to continue execution correctly. The first type is called structural hazard. It happens when the processor does not have enough hardware resources to execute multiple instructions simultaneously. And a common example is when instruction memory and data are shared. And the load instruction needs memory access, and the next instruction may also need memory access in the same cycle. And here you can see the cycle, and here in cycle 4, the both instructions want to use memory, which causes a structural hazard. And this hazard can be avoided by adding a separate instruction or data memory, or by inserting a stall. The second and most important type is the data hazard. Data hazard occurs when an instruction depends on the result of a previous instruction. And there are different types of data hazards, but the most common one is read after write, also known as row. Instruction 2 needs the value of register R1, which is produced by instruction 1. However, instruction 1 writes the result only in the write back stage. So here in the cycle, you can see that instruction 2 tries to use R1 during its execute stage before instruction 1 has written it, which causes a data hazard. One simple solution is stalling. The processor inserts a bubble, also called NOP, to delay the dependent instruction. And stalling guarantees correctness, but it reduces performance because the pipeline is no longer fully utilized. A better and more efficient solution is forwarding, also known as bypassing. Instead of waiting for the write-back stage, the result is taken directly from the execute or memory stage. And this allows the instruction 2 to use the correct value without stalling the pipeline. The third type is the control hazard. This hazard occurs due to branch or jump instructions. When a branch instruction is executed, the processor does not immediately know which instruction should be fetched next, and as a result, the pipeline may fetch the wrong instruction. If the branch is taken, the incorrectly fetched instruction must be flushed, and the solution for this could be control hazards can be reduced using stalling, branch prediction, or delayed branching. To sum up, pipeline hazards reduce the efficiency of pipeline processors. Structural hazards are caused by hardware limitations, data hazards by structural dependencies, and control hazards by uncertainty in bridge decisions. Thank you for watching.